Well, here we are. Congratulations. You've made it through almost the entire course. All that's left is we need to take a final exam. And the final exam is cumulative. So the idea is to keep in mind any cumulative final exam is going to cover all the big ideas. Um, and so what I have done is I have brought up the course competencies for us to go through and talk about so you can kind of see what is prescribed to us as a college, as what's important. What are we told to say? Make sure you cover this. This is what we expect students to know when they come out of your class. And this is agreed upon by ASU, U of A, NAU. This is all the stuff that all of our local colleges that we transfer most of our students to have all said is important. So as we go through this, you'll see it's kind of broken up into two parts. The first part is the big ideas. And up here, they're just saying, like, for example, number one, find the derivatives of a function using both the definition and theorems. Then it's followed by Roman numeral 1. So if you go in here to Roman numeral 1, this is the breakdown of what that is saying. So what this is telling me is find the derivatives of functions using both the definition and theorems. So we need to understand limits. So why do we need to understand limits? Well, if you remember the definition of a derivative, that was the derivative of a function is equal to the limit as h approaches 0 of f of x plus h minus f of x all over x plus h minus x. So if you remember, there's your formal definition of the derivative. And we need to understand limits to be able to talk about why is this true, what's happening. When we actually substitute in our values, we need to have h approaching 0, when we need to simplify. And so you can go back and refresh all of that if you'd like. And we needed to understand the concept of slope because this is just the slope formula. And we also need to understand, and then that leads us to the definition of the derivative. Then, once we got done with the definition of the derivative, we then went on to the rules of differentiation, where instead of doing all of it this longhand way, we learned about the product rule, the quotient rule, the chain rules, the implicit rules, implicit differentiation, related rates, and then higher order. When we say higher order, we mean second derivatives. What do they mean? How do they describe a graph? All that kind of stuff. So just in this first Roman numeral, it was just how to find them, how to find a higher order, how to do a second derivative. Okay, then comes number 2, using the derivative to analyze application problems related to business, life, social sciences. So Roman numeral 2. So what is that getting at? Applications of the derivative. Talk about where you have increasing and decreasing functions. How do you use a derivative to determine if a graph is increasing or decreasing? Well, hopefully remember, that's the first derivative, right? It is increasing if your first derivative is positive, and it is decreasing if your first derivative is negative. How do you test for extrema? How do you find mins and maxes using your first derivative? So remember, that was the first derivative number line test, where if you had where your derivative is equal to 0. So let's say we have some kind of function x squared plus 2. So therefore the first derivative would be equal to 2x. And we say, all right, where is this thing equal to 0? Well, it's equal to 0 at 0, right? Then I need to test my derivative on both sides. I need to test here if it was positive and negative. That means my graph is increasing to decreasing. So it's a max. Or if it was negative to positive, well, it means I'm going down to going up, which means it is a min. And a really funny happy face. There you go. Look at that. Anyway, so remember how to do that. Remember how to use a first derivative to talk about maxes and mins. Also, how do you use concavity, aka the second derivative test? What does it mean if I have at that point, if my second derivative at 0 is 4, that means it's concave up, right? So therefore it's positive, which means it's a minimum because it's concave up. Or if I had a negative 2, for example, then it's concave down, which means it's a max, right? So again, how do you use, not just find first derivatives, find second derivatives, but how do you use them? How do you use them to answer questions about optimization? And then the applications to business, life, social sciences, including velocity and marginals. So how do we talk about the marginals? How do we find marginal profit, marginal cost? and just hearing, oh, that just means derivative. It's the change in the production to the next item. What is velocity? How do you find velocity? Well, that's just the first derivative of the position. Second derivative is the acceleration. So it's that kind of stuff. And then business. When we talk about applications to business, what we're focusing on is profit, cost, revenue, putting those equations together. Okay, so that's item number 2. So the big ideas from here kind of, I hope it kind of makes sense. You're remembering all these big ideas. All right, item number 2 done. 3, use technology to model, solve, analyze problems related to real-world applications. So the idea of if the numbers get super messy or super hard, or the solving is absolutely ridiculous, can you use your graphing calculator to just do it for you, help you with it, know how to do that to get you through, so you can still answer the questions, but you don't have to do crazy hard solving, or you don't have to necessarily be able to find where one derivative is equal to another derivative. Nah, you just let your calculator help you with that. Okay, and that's for the first half of the class. Number 1, number 2, number 3, all covered. Oh, I forgot to do it down here. Number 3, using technology to model and solve problems. So we go down here, Roman numeral 2. So the idea is we can this stuff by hand or this stuff using your calculator, just depending on the level of ugliness of the problems. Then Roman numeral 4 is not related to this. Just all they're saying here is applications to business life and social sciences. The other parts are not from the first half of the class. Okay, now that's all chapter 2. That's all chapter 2. Those are your big ideas. And I'll walk you through. I've got another list here that I kind of made as I was writing the test of things to make sure you know how to do. But so anyway, do you guys, I'm hoping what you're getting out of this is the big ideas. What were the things prescribed to us? These are the things you better know how to do. I promise you they will be on the final. Absolutely will be on the final. Okay? Now, let's go on to the second half of the class. So that's the derivatives portion. So now let's go on to the integrals portion. That's going to be number 4 and 5. Okay, so looking at number 4, it says find the integral of a function using theorems. Okay, so when we say finding an integral of that's Roman numeral 3. So the antiderivative and indefinite integrals, including substitution and integration by parts. So essentially, can you use your derivative rules, your integration rules to find antiderivatives? And you need to know how to do substitution and by parts. Okay. Also, definite integrals and the fundamental theorem of calculus. Okay. So do you know how to not only find the antiderivative, but know how to evaluate it over some set of bounds? And do you know how to apply the fundamental theorem of calculus to that, which is the whole idea of just the integral of f of x dx is equal to going from bounds of a to b is the antiderivative evaluated at b minus the antiderivative evaluated at a. That's your fundamental theorem of calculus. And can you handle improper integrals? That was this last thing we just covered, where instead of going from definite bounds, you might be going from a negative infinity to a b or something like that. And that's where we use the limits and all that. So make sure you practice that. That's going to be important for the final exam. Okay, or it must be covered. It has to be on there. Okay, so then bringing us on to the last section here. Word problems using the integral to solve, analyze application problems related to business, life, social sciences. So this is where we talked about the area between curves, and the area under the curve, and understanding what does an integral mean. Area under the curve. How do you find area between two curves? And then of course applications. That was your the present value and the future value and the whole producer surplus problems from 3.7 and the consumer surplus and the equilibrium and all those types of problems. So make sure you practice those, because I promise you they have to be on the test. It's something that's prescribed to us. Okay, so reading through this, those are the big ideas. That's everything that is required for us to be on the test. So sometimes students ask me, well, will this be on the test? Will that be on the test? Well, I always say refer to this and say this is going to be the bulk of your problems. What types of things do you see missing from here? For example, there wasn't a big focus here on doing Riemann sums. There wasn't a focus on the left approximating, right approximating rectangles. So what does that mean about your final exam? Yeah, you guessed it. Probably not on there. Or if it is, it's going to be one problem. And your final exam, I believe, is 24 problems. So it's going to be very, very minor. So use your time effectively. Make sure you get these ideas, okay? These are going to be the bulk. Like I remember off the top of my head, just doing limits, just talking about limits, I think there's 5 of them. Right, 5 of those. And then how many Riemann sum problems are mentioned here? None. So therefore there may be one, probably none. Okay, so I hope that kind of gives you an idea how to study. Now, you'll notice the other thing I have done is gone through, and as I was writing the test, I was writing down big ideas from all of chapter 2 and all of chapter 3. What are the big things you need to know how to do? And I said every single, what do you need to do? Every single thing below. You need to know the theory behind it, not just be able to do it, but be able to use it, understand what it means. So when you find a derivative, be able to talk about what does it look like on a graph? What does it mean to me if it has a context, at instantaneous rate of change? Well, that would be a speed maybe, or so you just need to be able to make sure you can talk about everything. So don't just know how to find an answer, but be able to interpret its meaning as well. So for chapter 2, our big ideas here were the first thing, and this isn't major, it's actually almost all review, but if I give you a set of data and I ask you to make a function, know how to use your calculator to make a regression. Okay? So if they ask you to come up with an equation, you need to know how to use your calculator to do that. And that was from like section 2.1. We did that in there. All right, so then the next key thing, can you calculate limits? I believe, like I said, there's 5 of these on the test at least. I think there's 5 problems that are just limits. Then if I give you an improper integral, you need to use limits in there. And for your limits, make sure you understand some of your limits. My pen is acting up, I apologize. Some of your limits will be, for example, as x approaches 0 from the right, or 0 from the left, or could be approaching infinity or negative infinity. So you got to be ready for any from the rights, from the lefts. So really make sure you go back and remember your limits, and don't just remember how to calculate them. Make sure you remember how to interpret them. So what I would highly recommend is think about on every single problem, what does it look like as an algebra problem? So like, can I do a limit as x approaches 2 of, and then think about what would it look like algebraically? Well, that might look something like this. And so do I know how to do that? Yeah, I just substitute in the 2. And what if I can't substitute in the 2? Then what do I do? And you have to remember the factoring, and this problem doesn't factor because I just made it up. But can it factor, or then if it doesn't factor and I can't simplify it, then I need to test it from the right and test it from the left, see if it approaches the same number. So that's what algebra looks like. But what if, instead of algebra, what if I gave you a graph, right? So the idea here, what I'm getting at, is try to see if you can do every problem that you're going to go over if it was a graphical representation, if it was a algebraic representation, or formulaic representation, however you want to think of it. Try to think of it in all your different representations for studying. Okay? Can you calculate, now this is a big one, an average rate of change, okay, graphically, using, like if I gave you data points for modeling, if I gave you actual models as far as like an equation, can you calculate average rate of change? And the key thing people have to remember, average rate of change is just slope. It's not calculus. Average rate of change is linear, or is algebra. It's MAT212. It's just slope. So you're using just y2 minus y1 over x2 minus x1. For average rate of change, you need 2 points. Right? 1 point is not enough. You need 2 points to get an average. So if we're talking about it graphically, and we're saying, I don't know, here's point A, value A, here's value B. The average rate of change is the slope of the secant line. It's the slope that connects the two dots. How does that compare to the instantaneous rate of change? Well, instantaneous rate of change is 1 point. That is the slope of the tangent line. That's the idea of, if I'm looking at just this spot, the tangent line looks like that. So therefore, what's the slope of that line? Make sure you can talk about what that means. Average rate of change takes place over time. It takes place over from point A to point B, or from 1992 to 1997. What was the average change? Where instantaneous rate of change is at 1 point. You're not going to have a span of time. It's just going to be at one instant. Hence the concept of instantaneous. There are questions on your final exam. I always remember this. Where you have to be able to know which one you're supposed to be looking for. And it's just by how the question is asked. If it's asking for over a period of time, hey, that's average rate of change. If it's asking for a rate of change at one instant, then that's an instantaneous rate of change. And how do we find instantaneous rate of change? Slope of the tangent line, or AKA the derivative, right? Do you know your notations for instantaneous rate of change? Try to remember all your derivative notations. You've got the prime notation, you have the dy dx notation, you have the lowercase f of x is equal to the derivative of your uppercase f of x, right? So remember, you can go capitals to lowers that we learned in chapter 3. So just be comfortable with all your different notations. Then the idea of differentiability, if they ask you if something is differentiable. Now, this is going to be extremely minor. I would not worry about this too much, but the idea of differentiability, is it continuous, right? Are there any breaks, any jumps, any holes? Then if there's sharp corners, then it's not differentiable. But nonetheless, that wasn't really from the big list of things from down below. And so I would be shocked if there's anything about differentiability on the test, or if there's going to be like a minor 1 point something on the final. Can you graph a function compared to the rate of change graph? So the idea of the derivative. Can you say, here's my original graph, here's my derivative graph, here's my second derivative graph, and to be able to relate the two. That's just the whole idea of instantaneous rate of change. But instead of just doing it by hand and doing the formulas, this would be the graphical version of it. Okay. Just derivative formulas. Not only do you need to be able to look at graphs and see what the derivative looks like, but you need to be able to do the derivative. You need to be able to do product rules, quotient rules. You need to be able to do chain rule, which is missing from here. You need to be able to do the chain rule. Finding relatives, mins, and maxes, we already talked about that. Concavity using second derivatives, interpreting a second derivative. What does it mean? Meaning of an inflection point. How do you find an inflection point? Well, that's where the second derivative is equal to 0. So then you use your second derivative test, right? And you say, okay, it's equal to 0 at, I don't know, point C. It doesn't matter, whatever value it is. That's what made it equal to 0. So then you've got to test both sides of it on the second derivative and say, if it's concave up to concave down, then we have an inflection point. So yes, but if it doesn't change, if it goes concave down to concave down, then you don't have an inflection point. So make sure you really understand how to find inflection points. And then the meaning of inflection points, we didn't push too much in this class, but the big idea, if you stop and think about what's going on here, it means we have a change in concavity, right? So we have a 0, then we get steeper, then we get steeper, then we get steeper derivatives. Then at some point at the inflection point, we're as steep as we can possibly go, because then we start to get shallower, shallower, shallower until we're back at 0. So if this is the steepest slope, then what does that mean? What does it mean to be the steepest slope? Well, what that says to me is, well, if it was, let's say, a position function, the derivative of that would be speed, it would be velocity. And if that's where it's steepest, well, then that's where you're going the fastest. So a lot of the meaning of inflection points, you can actually, I want you to actually just be able to come up with on the fly. You're not going to memorize those. You're just going to have to say, well, think through it critically and develop your thoughts during the test and say, well, if the derivative is, has whatever meaning, then what would the what's going on with the derivative at an inflection point, and you can figure that out. Okay, and then finally, marginal analysis, right? Remember marginal analysis, that was a simple concept of just meaning cost to produce the next item. There we go. That, I think, fixed my pen. And how do you find marginal analysis? Well, that's the same thing as just finding the derivative. It's code word for derivative. All right, that was chapter 2. Chapter 3, way more straightforward. Way more straightforward. Just, do you know your integration rules? Can you find antiderivatives? Can you do integration by parts and substitution, those two techniques? Can you apply the fundamental theorem of calculus, which we already talked about before? Can you find an integral with a definite integral or an indefinite integral? And the key thing to remember about indefinites is after you do your integral, whatever it may be, you have to have plus c, right? Because we don't know what the person's doing with it. Where a definite integral has bounds, so you don't have to worry about it. You just apply fundamental theorem of calculus. Can you find the area between two curves? Remember, that's just finding the differences of the two functions. You subtract them, then integrate. Basic financial formulas, compound interest, continuously compounding. But more importantly than that was just the present value of a continuous income stream. So that's where we had our function of the integral from 0 to some time of whatever the function is for our continuous income stream times e to the negative rt, I do believe, dt. And I guess this should be f of t, not f of x. So just being able to find that present value, interpret what that present value means, and going from there. And then, of course, the one thing that's not covered in the book that we had to add on ourselves is just the improper integrals. And on those, just understanding that means you're integrating from over a vertical asymptote, you're integrating over a 0 or something like that, dividing by 0, or integrating towards infinity. And that's where we just use the limits. So at this point, the only difference between this study guide and the study guides before is in the study guides before, I went through and picked problems out of the book. Well, you already have my study guide for the first half of the class. So I'm hoping you at this point are a strong enough student where you can do this yourself now that you've seen my study guides, you've kind of seen how I build them, and you can do this for chapter 3. Really, what do you need to pull out? Integration rules. Practice, 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 practice. Just pull out problems from the book. Just look up any integration problem you can find. Do those worksheets I gave you. Just practice your integration. And integration by parts and substitution, again, practice those worksheets. Fundamental theorem of calculus, yeah, really? Okay. Definite integrals, indefinite integrals, well, hey, that just got practiced when you're doing the integration from before. Area between two curves, yeah, not too hard to figure out some problems there, because all we're doing is just you can almost make them up yourself and test them in your calculator. And so the only ones that are not really formulaic, the ones that are a little more thinking based, is just these last two. It's the basic financial models, which is not really so much. It's really the present value and the continuous income stream of the continuous income stream. And the one thing that is actually missing from here I need to add on would be the whole producer surplus, those ideas, and the whole equilibrium, point of equilibrium. So make sure make sure you go and pull some problems out of the book, practice those, and remember, in Math there are the solutions to selected problems, and you can always email me your work, and I will gladly check any problem from there. But here we go. So you can see here's our chapter 3 answers, so we can go ahead and check those out. And yeah, pick problems from the book. You can see there's some stuff from 3.4, there's some stuff from 3.6. So pick problems from the book, practice them, make sure they're making sense. Don't just do your homework problems. Should you go back and review your homework problems? Absolutely. Is that enough getting you ready for the final? Absolutely not. Okay? And pick some problems, practice some problems, and the key thing, don't cram. Don't cram. It never goes well if you cram. Space it out. Practice a section each night. Pick a problem from here, pick a problem from there. Do a little bit every night until the final exam. Just as a reminder, I'm making this video during the fall 2015 semester. But this would be true for any semester. Go to your syllabus, look at the calendar, and you will see the final exam dates. So your final exam, proctored final exam, the dates for the fall 2015 semester go between December 9th and December 14th. This is a proctored test, so you either need to come take it in the Math Q Building Testing Center, or schedule a time with ProctorU, and you'll have to pay whatever fee that is to take the test through them. But go ahead and schedule your test and plan to take it between those dates. And of course, if there's any issues, you're always welcome to ask me, and I will try to accommodate anything I can accommodate. If I am teaching this class in person and you would like to come take this final exam with my in-person class, I'm sure I can work something out. It's your call. It's whatever we can work out. I would love to do for you. I'm here for you. So now is time for you just to start studying. Best of luck.